All right, we're going to start section 7.3 today. We've been discussing in this whole chapter about sampling distributions, and the last section we talked about how to use sampling distributions to estimate a sample proportion, and now we're just going to shift gears and look at how to use a sampling distribution to estimate a sample mean, or a population mean rather. Okay, so here's what we know. We know that sample proportions arise, particularly when we're interested in categorical variables, things like maybe the proportion of orange candies in a candy machine. Oftentimes the thing we're measuring is not numerical, and so we're counting the proportion of that particular item in a given sample. But with a sample mean, that's when we're interested in a quantitative variable, okay? And this is when we could calculate other statistics like a sample standard deviation or a sample median. Okay, we would have worked through a couple activities prior to this particular notes page where we were sampling and estimating from a large population of pennies, I believe, trying to hone in on exactly what the mean population year was. And then we also looked at sort of how the shape of the sampling distribution adjusts and changes based on whatever the population distribution is, okay? So here's what we hopefully were able to conclude from those activities, that if your population distribution has a shape that is normal or even just approximately normal, okay, then the sampling distribution for X bar will have a shape that is approximately normal. Okay, and that feels like that should make sense. If the population's normal, the shape of the sampling distribution would be normal, and that does not matter at all on what the size of your sample is. Okay, it could be small sample sizes or large sample sizes. If you're pulling it out, it needs to be consistent though when you're doing a sampling distribution. When you're pulling it out of a population that has a shape that's normal, you can expect the shape of the sampling distribution to be approximately normal. Okay, the other thing that we were looking at is that as the sample size does increase though, how that affects your standard deviation for your sampling distribution is it definitely causes the standard deviation to decrease. Okay, the standard deviation decreases. So it really starts to shrink in much closer around where that true population mean is. We can see this kind of pictured here below. Okay, on these few graphs here, it says the display on the left illustrates the distribution income of the population of 61,472 households. Suppose that you were to take simple random samples of size 100 from the population and you calculate the sample mean. The sampling distribution of these sample means is illustrated here below. Okay, so we can see here that this is suggesting that the distribution of earned income in the population, here's what we have. So this is the population distribution. Okay, this is the population distribution, which kind of feels like that has almost a right skew to it. And then over here, this is the sampling distribution. If you took samples of size 100, you calculated the average income of each of those samples. And you'll notice that here we're getting what looks like approximately normal. Okay, and this is something that we looked at in our other activity where, in fact, the shape of your population distribution doesn't have to be normal. It can actually have a skew. But then when you go to do the sampling distribution is going to come out approximately normal. Okay, provided you've got a nice large sample size there. But what I want you to notice just in this picture, and we'll look at that a little closer here, is that the variability of your sampling distribution, it is much less than the variability in your population distribution. Even though they're both centered right here on the same spot, you can see where mu is located. You can see how there's a lot more spread in the population distribution and much, much smaller spread in your sampling distribution. And that's because when we average, which that's what this is a sampling distribution of, averages are a lot less variable than the individual observations that we'd be seeing there in our population distribution. Okay. So we have a couple of formulas here. These are both located on the formula sheet. How to find the center of a sampling distribution for x bars or means. Okay, and this is a pretty simple formula. The center of your sampling distribution for x bars should land directly on top of whatever that true population mean is. And in terms of the spread, the standard deviation for sampling distribution of sample means, you take the population standard deviation and you divide it by the square root of whatever the sample size is. Okay, now remember, when we are talking about finding the standard deviation, this is the 10% condition. The sample size must be less than 10% of your population in order for you to use this formula here. Okay, that's the 10% condition. Okay, a couple things I'm just going to highlight here underneath. Okay, the sample mean is considered an unbiased estimator for your population mean if you are taking your simple random samples properly. It needs to be random. It needs to be good sampling techniques. Okay, the other thing that I'd like for you to circle or highlight is if you ever are needing to quadruple your sample size, okay, that's going to result in your standard deviation being cut in half. And I want you just to look at the formula here and see why that is. If I were to take this formula, but instead of my sample size being n, my sample size is 4 times n, so I am quadrupling what the sample size is, you'll notice I now have a 4 underneath the radical. The square root of 4 would be 2, so I can pull that 2 out. And now if you look at what we have here, essentially I can put that fraction 1/2 just in front of my formula, and that is now causing what would be the standard deviation for my sampling distribution of x bars to now be cut in half or multiplied by 1/2 here. Okay, so let's take a look at an example here. Okay, in this example, it says the height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. Now, what I want to draw your attention to on this problem is that this is specifically asking for just the probability of a single observation. So what we're suggesting here is that if we had, all of the young women in a hat and we simply selected just one of them, we're not talking about drawing out a sample, we're just taking one, only one out, okay, not a large sample size at all here. Okay, so let's write down what we know, and this is what we know about the population distribution of these heights for these young women. Okay, it mentions that it is a normal distribution. They give us the mean and they give us the standard deviation. So I'm going to go ahead and abbreviate all of that information here. Okay, the question that is being asked is, what is the probability if you were just to select one young woman from this population, what's the likelihood that she would be taller than 66.5 inches? Okay, so I'm going to use normal CDF. Okay, I'm going to have a lower bound and an upper bound. Lower will be 66.5, upper bound will be 10,000. The mean, I'm using the population mean, and the standard deviation, I'm using the population standard deviation. This is going to come out to 0.2119, and I'm going to go ahead and draft a little interpretation here so we can see the difference between this and what the next part of this problem is asking. We're going to say that there is a 21.19% chance that A, okay, I'm emphasizing that this is just singular here, that a randomly selected young woman is taller than 66.5 inches, okay? It's taller than 66.5 inches. Now, let's look at what the second part of this is asking. It says, find the probability that the average height of a simple random sample of 10 young women would exceed 66.5 inches. Now, there is a huge difference between what these two parts of this problem are asking. Now this is asking, if you were to select a sample of 10 young women, what's the likelihood that the average of that sample would be larger than 66.5? So we want the probability of an average of a sample. Okay, you'll notice they put the word mean there and not a word like a for singular. Okay. So if we're going to calculate the probability that the average is greater than 65, okay, and I'm going to go ahead and fill in, this no longer is x, but rather that x bar is greater than 66.5, I'm going to need to calculate a few things here. Okay, I'm not going to be able to use this information here for my population distribution. I'm going to need to construct what the shape and the center and the spread would be for the sampling distribution. Okay, so let's go ahead and see if we can work through this here. We're going to start with the center. Okay, and here's what we know, and this was listed up above. To get the center of your sampling distribution for x bars, that should be right in line with whatever we know the population mean height to be. Okay, well, they told us here that the population mean height, that's right up here in the problem, is 64.5 inches. Okay, there is no condition that you need to first show for anything regarding the center. Okay, for the spread, I'm going to be using the formula again that's at the top of the formula sheet, and that is, not the top of the formula sheet, top of this sheet here. That's to take the population standard deviation and divide it by the square root of my sample size. Okay, now before I get ahead of myself here and make that substitution, off to the side, I need to do the 10% condition to make sure that I'm not taking a sample that's too large without replacement, that I'm going to lose that independence condition. So I need to show that 10 times my sample size would be less than or equal to all young women. That's what my population is, all young women. And certainly 100 young ladies would be less than or equal to all the young women that exist. So I'm going to check off that that is met. Okay, so then we're going to go back. They gave us in the problem what the population standard deviation is. So I'm going to plug that in here for 2.5. My sample size is 10, so I'm going to plug 10 in there. And then we're going to type this into the calculator, and we get our standard deviation for the sampling proportion to be 0.7906. Okay, the last thing is we need to confirm what the shape is. Okay. Now, they did tell us that the shape of the population was normal. So here's what we know. We know since the population distribution is normal, then the shape of the sampling distribution is normal. Okay, that's what we know. If the population shape is normal, we'll talk about when it's not normal here in a moment, but we were told in this problem that the population distribution was normal, so we then can conclude that that is normal. So I'm going to go ahead and come over here then and abbreviate what I know. I know the shape is approximately normal. I know that the center is still at 64.5, but be careful, this is a different spread that we're using. We're going to use that for our spread. Okay, now we can come back up. We can use normal CDF. Okay, and it's going to feel like almost all of these inputs were the same inputs as what we put in for the previous problem, but the one that's actually different is what you're plugging in for the spread. Okay, and then the answer to this would be 0.0057. So for me to write kind of an interpretation here for this, I'm going to say there is a only 0.57% chance that a simple random sample of 10 young women would have, and this is important, would have an average height that is greater than 66.5 inches. Okay, you can see there's a big distinction here. Here we're talking about having a group of 10 women and their average height. Okay, that's what that probability is referring to versus the first problem. Okay, so let's go back and revisit this idea of shape, because that example was really looking at, we could say that the shape is normal if your population distribution is normal, but what if the population shape is not normal? Okay, so we go back and we think about our activity where we were kind of having the population shape maybe be dramatically skewed, or it could even just kind of be really bimodal or something like that. We learned that no matter what the population distribution's shape is, if you take a large enough sample, then the sampling distribution for your mean should have a shape that is approximately normal. Now, we need to come up with a way that we can say, what does large enough mean? Well, we're going to say a sample size that is large enough would be as long as you are taking a sample that is 30 or greater. Okay, 30 or greater. Okay, so that's what we were looking at down here, and we were seeing that if we took, let's say this was the shape of your population distribution, which is really wacky shape here, okay, very, trimodal almost. Now you'll notice if we only do sample sizes of size 2, and we calculate the average and we plot that on a dot plot and we keep repeating that, this doesn't feel very normal. There's still a lot of bumps along the way here. But look at what happens as I go even just to a sample size of 5 and then 10 and then 25, you can really start to see it even out, and that safety sample size that we use in statistics is a sample size that's going to be greater than or equal to 30. And this is called the central limit theorem. The central limit theorem says as long as you're taking a large enough sample size, greater than or equal to 30, your sampling distribution for your X bar will be approximately normal. Okay, and it's saying down here, this is in most cases, that's a pretty safe sample size. Okay, we try to stay away from anything smaller than that in order to be able to conclude normality here. Okay, so we're just going to take a look here at just a couple more examples to kind of wrap this up. You can see on the next page here then, just to sort of summarize the shape aspect, we have essentially two things that we could conclude normality for. One is if the population distribution is normal, we can just say that, and then therefore the sampling distribution for X bar would be normal. Or if the population distribution is not normal, like we know that it's skewed or it has an odd shape, we can still conclude that the sampling distribution for X bar would be roughly normal as long as the sample size was greater than or equal to 30. And anytime you're citing that, always make sure that you say then by the central limit theorem. Okay, so let's try an example that sort of puts this into action here. So suppose that the number of texts sent during a typical day by students at a very large high school follows a right skewed distribution. So we know the population shape is right skewed. It's not normal. Okay. The mean is 45, the standard deviation is 35 texts. It's asking us to describe the sampling distribution of sample means for simple random samples of size 20. And it mentions to check the conditions for each statement. So anytime you're describing a sample, any distribution, actually, you should always find the center the spread, and the shape. Okay, we know the center of the sampling distribution should be right in line with whatever the center is for the mean. So that'd be 45 texts. Okay, the spread, keep in mind this formula here is on the formula sheet. The spread is the population standard deviation divided by the square root of your sample size. Okay, but off to the side, I'm going to check the 10% condition. My sample size was 20. I need to show that 10 times 20 would be less than or equal to all students at this large high school. Now, they didn't tell us how many students there are at this large high school, but I think they used the word large, insinuating that it was a very, very large population. So it's probably safe to assume that 200 is less than or equal to all the students at a large high school. Okay? So I'm just going to check that off, and then I'm going to circle back, and I'm going to go ahead and plug in that the population standard deviation is 35, our sample size is 20. That gives me a standard deviation for the sampling distribution to be 7.826, and then we're going to go ahead and look at shape. Okay, now shape here, I know that the shape of the population distribution is not normal, so I can't conclude normality because of that. But if my sample size is 30 or greater, I could conclude normality. But if I look at this, since 20 is, and I'm going to put a slash through that, not greater than or equal to 30, we can't assume normality. Okay, and our conclusion probably is that the shape, it's likely right skewed because we just didn't take a large enough sample for the shape to be normal. Okay, so what that means is we couldn't move forward only taking samples of size 20 to try to calculate any probability question. If we increased the sample size and that allowed us to say then that the shape of the sampling distribution was roughly normal, then we would be okay with doing that. And that's what they're suggesting and wanting us to do here with part B here. So we're going to run through and fill out here what if the sample size was 50 instead of 20. Okay, and they want us to find a probability here of getting a sample mean of under 40 texts. Okay, so we're going to keep our center at 45. The spread is going to be different. It changes anytime your sample size is different here. Okay, so I'm going to do a quick 10% condition check over here. 10 times 50 should be less than or equal to all students at this high school, and I still think at a large high school, 500 is safe to say that that would be less than or equal to all of them. Okay, I'm now plugging 50 in for my sample size, and that's giving me a standard deviation of 4.9497. Okay. All right, now for the shape. Okay, I know the shape is still right skewed, but here's what I could do for the normality piece. I need to show that my sample size of 50 is greater than or equal to 30. I'm just going to abbreviate underneath that and say, by the central limit theorem, I can now conclude that the shape of the sampling distribution would be approximately normal. Okay, so I'm going to put all my information together, and for normal, 45 for the average of the text, and that would be my spread. Okay. All right, so now the question, part 4 here. We're looking for what's the probability, now read this closely here, what's the probability of getting a sample mean, that means an average of under 40 text for a sample of 50 kids. So I'm looking for what are the odds that an average, X bar, is less than 40. Okay, so I'm going to do normal, CDF. We're going to go negative 10,000 to 40. The mean is my 45, and the standard deviation is that 4.9497. Okay, this comes out to 15.62%. So we're saying that essentially the probability of selecting a sample of 50 students and the average of those 50 students being that 40 texts were sent out, is looking at about 15.62%. Okay. All right, the last problem that we are going to look at here on this video is just at the top of the next page here, talking about servicing air conditioners. It says here, based on many service records from the past, the time in hours that a technician requires to complete preventative maintenance on an air conditioner follows the distribution that is, oh yeah, that looks like it is strongly right skewed. Okay. It says the most likely outcomes are 0 hours. Okay, so they're getting it done in under an hour. That's why this is much higher over here. Okay, it says that the mean time for the population is 1 hour. The standard deviation is 1. Now, it mentions here that your company is going to service a simple random sample of 70 air conditioners, and you have budgeted 1.1 hours per unit for repair. The question is this going to be enough time per unit? So we're averaging 1.5 hours per air conditioning unit. Okay, what is the chance that these technicians are not going to finish within the time frame? Okay, so we can tell this problem is talking about a group of things, a sample, and so that's when we're referencing a sampling distribution. We first need to find the center and the spread and then the shape here. Okay, so our center should be right on whatever it said the population mean time is. That's 1 hour. Our spread, okay, this is our formula. I'm going to run off to the side here and do the 10% condition. Okay, 10 times 70 should be less than or equal to all the air conditioners that this company services. It's probably safe to assume that this company definitely services, more than 700 air conditioners. Okay, so I'm going to go ahead and go back and plug in 1 for the population standard deviation, 70 for my sample size. Okay, and now for normality. I know I can't say that it's approximately normal because the population distribution is normal, because that's strongly right skewed. But as long as my sample size, which is 70, is a number greater than or equal to 30 by the central limit theorem, I can conclude that the shape is in fact approximately normal. Okay, so now I can go ahead and move forward with answering the question. Okay, the question is, what's the probability that the average time that it would take to repair an air conditioner is going to be, now the reason I'm choosing greater than is because it says what's the chance that he wouldn't be able to finish in the time frame, and they've allocated 1.5 hours per unit. So I'm looking for what are the chances that the average is more than 1.5 or 1.1 hours per unit here. Okay. All right, so we're going to fill in 1.1, 10,000, 1 is the mean, and 0.1195 is the standard deviation. Okay, and the chances are 20.13% that he would not finish in that time frame. All right, you can see a few problems there for you to try that go along with this video.